Hi everyone and welcome. We move on now to chapter 15 on fluid mechanics. And on the slide you can see a picture of a pressure gauge, such as one that might be used to measure the air pressure in your car tires. And we also see a picture of Archimedes in the bath. Archimedes was a scientist around 300 years before Christ. And the king, he gave Archimedes a challenge. The king said to Archimedes, I want you to test my crown and make sure that it's made out of pure gold. But the catch is you aren't allowed to destroy it or damage it in any way. And Archimedes was wondering how he could go about solving this problem. It was something that was bothering him, when one day he was sitting in the bath and he came up with a solution. And the story goes that he shouted out the words "Eureka," which means I found the answer, and he was so excited he jumped out the bath and ran down the street without any clothes on. And the solution that he found was based on Archimedes' principles, which is one of the topics that we're going to be covering in this chapter. Alright, so here we have the learning outcomes for this chapter. You can see that there are a number of definitions that you need to know. Then you need to know a little bit about how pressure is measured and what units we use to measure that. You should be able to derive an equation for the pressure at any depth within a fluid. And then also there are two key principles. The one principle which you should know is Pascal's Principle, as well as Archimedes' Principle. And you need to know firstly you need to know what each of these principles are, and then we also need to know how to apply them to solve problems. So then we start with the definition of a fluid. A fluid is a collection of molecules that are randomly arranged and held together by weak cohesive forces and by the forces exerted by the walls of the container. Both liquids and gases are fluids. I think that's an important point, that both liquids and gases are defined as fluids. In everyday language, we may not think of gases as fluids, but scientifically speaking, they are. In terms of the definition for fluids, an important point is that the forces between the molecules are weak cohesive forces, so they're relatively weak. And then we also have forces exerted by the walls of the container. In school, you would already have looked at the models describing the physical properties of matter, and we had a description of each of gases, liquids, and solids. So we look quickly through those definitions and those points for the models of the properties of matter. Starting with gases. Gases consist of fast-moving molecules, and the molecules, they're all moving around within the container, and they're colliding with one another as well as with the walls of the container. As the particles are buzzing and moving around, bumping into different things, bumping into the walls of the container, they exert forces on the walls of the container every time there's a collision, right? So this leads to pressure on the walls of the container. And the force that's exerted will then also depend on how fast the molecules are moving. If we look then at liquids, we can see that the molecules are moving randomly around, similar to with a gas. But for liquids, we find that the speed of the molecules is much slower in this case. And because of this, a liquid has a higher density than gas. If the molecules are moving slower in a liquid, it means they're closer together, resulting in a higher density. The pressure increases with depth in a liquid. So that's to say, if you start at the top of this container and you move yourself down to the bottom of the container, then you'll find that when you get to the bottom, the pressure will be higher than at the top. And the reason for that is because once you get to the bottom, you're going to have a column of liquid which is pressing down on you, and that increases the pressure. At a fixed depth, the the pressure is uniform at all points. So that's to say, if we're at this depth, then wherever we are at this depth, the pressure will be the same. Liquids exert pressure sideways on the walls of a container, unlike a solid. So that makes sense. If you have a liquid, it will be pressing against the side of the container. If you think of a dam, for example, if the dam has a weak wall, then the pressure of that liquid might in fact break that wall. And this is, due to the molecules that are moving around within the dam and bumping against the wall of the dam. Let's get back to the definitions again then. One definition that you'll already be familiar with is that definition of density. And density is the mass of an object divided by the volume that mass will occupy. For solids and liquids, the density is constant at a fixed temperature, whereas the density of a gas, it depends on the volume of the container that it's in. And the reason for this is that a gas will expand or contract to fill the complete volume of the container that it's confined in. So that's the definition of density. We also have a definition of specific gravity, and specific gravity is defined as the density of an object divided by the density of water at 4 degrees Celsius. So it's, if you can think of it as the density of an object relative to the density of water at 4 degrees Celsius. And in recent years, or maybe years gone by, it was important to test car batteries to find out if they're still working well and still holding their charge. And people would actually measure the specific gravity of the electrolytes, the liquid in a car battery. And the reason for that is that because the specific gravity of the battery electrolytes, it decreases linearly with voltage. So there's this linear relationship. So if you could know the specific gravity of the electrolyte, you could know the health of the battery relating to its voltage. With relation to density, we see that density is measured in SI units of kilograms per cubic meter. Remember, it's mass per volume, so it's kilograms per cubic meter. Important for us to note is that we see that the density of water is 1,000 kilograms per cubic meter. So if you have a cubic meter of water, it has a mass of exactly 1,000 kilograms. An interesting phenomenon, you can see the density of ice is 917 kilograms per cubic meter. So you find that the density of a solid, ice, is actually less than its liquid form, water. And this is something a little counterintuitive, as you might expect the density of solids to be greater than that of liquids. But the reason for that is because of something called hydrogen bonding. And it's actually quite an important phenomenon for nature, because what happens is you might have a pond, and as the temperature decreases, then let's think of a case where ice actually had a higher density than water. As the temperature would decrease, the top layer of the pond would freeze and form a layer of ice. If ice's density was greater than water, you would find that layer of ice would sink to the bottom of the lake. Then the top of the lake would freeze over again, and that layer would sink to the bottom. The process would repeat itself until you find that essentially the whole lake will be frozen solid, and all the fish and animals in the lake will die. So that's what would happen if the density of ice was greater than that of water. But because of hydrogen bonding, and because of the density of ice being less than water, we find that ice actually floats on water. So what happens then is in winter, if the temperature drops below 0 degrees Celsius, The top layer of water, it freezes, it becomes ice, but that ice in fact floats on the water because the density of the ice is less than the density of the water. And that top layer of ice, it acts as an insulation, which insulates the rest of the water below it from the low temperatures, and it prevents the whole ice, the whole lake from freezing solid. The next definition we have is that of pressure, and pressure is equal to force divided by area, where F represents the normal force. So that's the force acting at 90 degrees perpendicular to the surface. And A is the area on which the force acts. The SI units of pressure is going to be newtons per square meter, because force is in newtons and area is in meters squared. Newtons per square meter, we also call that a Pascal. So it's also represented by the units of Pascal. So if you hear of 1 Pascal, then we're referring to 1 Newton per square meter. Shown here is an example of a force of 100 newtons being applied in each of these 3 cases. But in the 3 cases, it's been applied to different areas. So you can see here it's applied to 4 square meters, here it's applied to 2 square meters, here it's applied to 1 square meter. And you can see as the area gets smaller, applying the definition, you can see that the pressure gets bigger. So it increases from 25 pascals in the first case to 100 pascals in the final case, or 100 newtons per square meter. Think for yourself an example. If someone stands on your toe, right? Perhaps they're wearing slip-flops or sandals. In that case, it's not going to be so painful. Whereas if they're wearing high heels or stilettos, if the same person stands on your foot, it may be very painful. And the idea with that is the same force, the person's weight, is now being applied over a much smaller area. So we have a much smaller number in the denominator, and this results in a high pressure on your foot, which increases the pain. For the slip-flops or sandals, the area of contact between the sandal and your foot is going to be much bigger. So because it's a bigger area, we have a bigger denominator term and a much smaller pressure. So in that case, it will be less painful. If we look at units of pressure, we've already seen that the SI units of pressure is Newton per square meter, and we also call that a Pascal. So 1 Pascal is 1 Newton per square meter. If you measure the atmospheric pressure at sea level, then you find it's given by 101,325 pascals. So it's around 101,000 pascals. That's the pressure at sea level. We often give this pressure another name. If it's 101,325 pascals, we refer to that as 1 atm or 1 atmosphere. So if you hear 2 atmospheres, then you know that the pressure they're referring to is 2 times this number here. 1 atmosphere is also referred to as 1 bar. And often we'll use this terminology when we go to the garage to have the pressure in our tires checked. You'd say, can you please check the tires and make sure that it's 2 bars or 2.2 bars. So what we're referring to is twice the atmosphere, or 2.2 times atmospheric pressure. 1 atmosphere is also represented by 760 millimeters of mercury, and the chemical symbol for mercury is Hg. Another way of saying 760 millimeters of mercury is 760 torr. And the reason we represent in pressure by millimeters of mercury, as you'll see in the next slide, we have barometers, and barometers work according to columns of mercury. And then if you working with people from overseas, you might often refer or hear of the PSI, and 1 PSI is 1 pound per square inch. But note that these aren't SI units. The pound isn't SI unit of mass, and the inch isn't the SI unit of length. So in our course, we won't be working with, you know, the PSI. Here's then a slide about how could we actually measure pressure. Well, if we wanted to measure pressure, we could do that by applying the definition. We know that the pressure is the normal force per unit area. So this implies that if we wanted to calculate pressure, perhaps we could, you know, measure the force and then measure the area and just divide the two and find out what the answer is. Well, in practice, this is something that's not that easy to do. So we use indirect approaches to measure pressure. And one of those approaches is by using a barometer or a manometer. These are two devices which we can use to measure pressure. And as I've already mentioned, then we relate the pressure to the height of mercury in these devices. I'd like you to just take some time for yourself to read how manometers and how barometers work. We're not explicitly going to speak about that now, but if you look over it, you'll be able to follow the explanation. Specifically, the explanation is related to this equation here, which we're going to deal with in the coming slides. So now we look at a derivation that you need to know, and this derivation is to find a formula for the pressure at any depth within a fluid. So what they're saying is that we have some beaker or some container of fluid, and we're going to focus our attention on what they call a parcel of fluid. So this parcel of fluid is some small little block of fluid within this beaker. And what we're actually going to do is we're going to look at the different forces acting on this block. Remember, it's a three-dimensional problem, so underneath the block it has some cross-sectional area of A. And if we consider this little parcel with cross-sectional area A, note that it starts at a depth of D and it extends down to a depth of D plus H, right? And if we look at the forces acting on this little parcel of liquid, we have one force acting from above. This is going to be given by minus P naught A. So remember, P naught will be the reference pressure at the top. So we'll have minus P naught A acting downwards. Here, this represents a force because remember, pressure is equal to force over area. So force is area times pressure. We're going to have a force acting upwards given by PA. This is in the plus J hat direction. This P is what we're actually trying to find. Then there's going to be another force acting. This is going to be the force as a result of the mass of this parcel of liquid multiplied by G. That's going to be acting downwards, a force mg. And what we're saying is that these different forces are in equilibrium, so they need to add up to zero. The reason we say that is because this parcel isn't moving up or down. So we have this this force at the bottom, this one here, acting upwards. Then we have the force at the top. This is P naught A, the atmospheric pressure times A, acting downwards. And then the third term is the weight of the liquid itself. So the sum of these three forces is zero. This then gives us this expression here. PA, the P is what we're trying to find, is equal minus P naught A is equal to minus density A GH. So what we've done to arrive at this third term is we've substituted in for the mass of the liquid. We've substituted in that the mass is the density times the volume, and the volume is going to be the area, the cross-sectional area, times the height, h. Again, this volume is going to be the cross-sectional area times h. So we substitute in for capital M over here to then give us this expression. So the final expression that we see is that the pressure at this point here, it's going to be equal to the pressure at the top, which is P naught, plus the density of the liquid times G times H, where H is this column of liquid. So the result we have then, if the liquid is open to the atmosphere and P naught is the pressure on the surface of the liquid, then P naught is the atmospheric pressure. So as we see, P naught will be this number that we saw before, 101.3 kilopascals. And an interesting consequence of this equation that we derived is you can see that the pressure is just a function of different parameters. That's P naught, the atmospheric pressure. It depends on the density of the liquid, and it depends on the height that we at. And this is an interesting result because in this equation there are no terms referring to the shape of the container. The pressure depends mainly on the height. We take a look now at this figure here with this fairly exotic shaped container, right? It has all these different shapes to it, and what we're interested in knowing is what is the pressure at different heights. So we have three lines. We have one line at the surface of the container, we have another line at depth HA, and a third line at depth HB. And what we find is, the pressure at the surface, it's going to be the same at each of these 3 points. It doesn't depend on the shape of the container. It only depends on the height above the surface. If we go at height HA, then the pressure at A is going to depend on the pressure at the surface plus the density times G times HA. That's a formula we've just derived. And the pressure is going to be the same at each of these 4 points. Looking at height HB, it follows the same form where the pressure, it's just a function of this height HB, and it's the same at each of the 4 points. So you can read, we can look through this caption. The pressure at any point in a stationary fluid is a function only of the height of the fluid above and the pressure at the surface. So it doesn't depend on the shape of the container. We take a look now at Pascal's principle. The principle states that a change in the pressure applied to a fluid is transmitted undiminished to every point of the fluid and to the walls of the container. Here the word undiminished, it refers to without getting smaller. So in this example, what we have is we have 2 pistons. A force is being applied to this piston here, right? Because this force is being applied, it means that the pressure is going to change within the liquid. But the change in pressure is conveyed throughout the liquid undiminished according to Pascal's principle. So that means that the pressure at every point in the liquid is going to be exactly the same. The pressure over here is going to be the same as the pressure over here. If you look carefully on this side of the experiment, we apply a pressure, with or a force F1, and it's acting on a piston with area A1, and this piston is moving down delta X1. On this side we have it's resulting in a force acting upwards, which is F2. It's acting over a bigger area. This is a bigger piston with area A2, and it's moving distance delta X2. So according to Pascal's principle, when we apply that, we see that the pressure is going to be the same everywhere. The pressure at this point here is going to be F1 divided by A1, and the pressure over here is going to be F2 divided by A2. These two terms are going to be equal because the pressure is equal. And as shown in this diagram, it refers to a hydraulic press. So what has happened, a vehicle undergoing repairs, it's supported by a hydraulic lift in a garage. And what actually happens is you'll have a mechanic who's applying F1. F1 may be a relatively small force, what will be a relatively small force applied to a small area. This results in a large force applied to a large area. The ratio of the two is going to be the same. So because the pressure is the same everywhere, we have a small force applied to a small area, resulting in a large force applied to a large area. And this actually allows the mechanic to lift this car, right? This hydraulic lift system, it almost magnifies his force. He applies a small force in, but he gets a large force out as a result of Pascal's principle. You might think that this sounds a little strange. How's that possible? Aren't we violating any laws of nature or laws of physics? And the answer is no. The main force that we need to, or the main law that we need to satisfy is that of conservation of energy. And over here we have a small force acting over a large distance. Remember that the work is going to be given by the product of those two. And here we have a bigger force acting over a smaller distance. So in both cases, the work done on this side will be the same as the work done on this side, but we find that on this side there's a much bigger force due to Pascal's principle. As shown on this slide, Pascal's principle can be applied to a number of different applications. We've just seen it, how it can be used in a car lift, it can be used in dentist chairs, hydraulic brakes, any similar systems. Here we have another example of how a hydraulic brake might work in your car. So what you would have is the brake pedal. At the brake pedal, you would be applying a relatively small force over a small area on the pedal, and then the hydraulic system will have a larger plate in contact with the wheel, a larger braking plate. And this will result in a large force acting over a large area. Remember that, and you know that will effectively stop the car because we have a large force. So remember again, what we have is the pressure being the same at each of the points in the fluid because of Pascal's principle. So that means that Fx over Fa, the small force over the small area, gives a large force over a large area to maintain that ratio. So let's have a look at an example of a problem to be solved using Pascal's principle. So the example relates to a hydraulic lift which is used to raise a motor car of mass 1020 kilograms. The diameter of the master cylinder is 2 centimeters and that of the slave cylinder is 10 centimeters. What is the magnitude of the force to be exerted on the master cylinder to lift the car? So over here I've made a drawing of the situation. On the left hand side we have the master cylinder with a smaller radius. The diameter is given as 2 centimeters. So that means that the radius is going to be 1 centimeter. And on the right we have the slave cylinder with the car and the larger radius of 5 centimeters. In engineering, they often use the terminology master to refer to the smaller cylinder and slave to refer to the bigger cylinder. The reason for that is that whatever happens at the smaller cylinder is going to dictate what happens on the right hand side at the bigger cylinder. So the information we're given is the radius of each of the cylinders, and we're given the mass of the car, and we asked to calculate what force needs to be exerted on this side to lift this car. So the approach that we follow is that of Pascal's principle. Pascal's principle says that the pressure on this side, the pressure on the master side, is going to be the same as the pressure on this side. So PM is equal to PS. We can rewrite pressure as terms of force over area, force over area. So we note that the force at the master side is going to be given by the ratio of the areas to the force that appears on this side. As I've drawn it, our cylinders are circular, so when it comes to calculating the area of each of these, we use the formula pi radius squared for circles. Just take note that in our question we're given the diameters of the two cylinders, but in this formula we need to use the radii. So that's why I've used the numbers to divide by 2. So it turns out then that the force to be applied on the left hand side is given by this expression here, and then we can simply substitute the values in, and we found the answer to be 400 newtons. So this means a force of 400 newtons needs to be applied on this side to lift this car. So in the coming slides we're going to be dealing with Archimedes' principles and floating objects. And in order for us to build some intuition about this topic, let's start by watching a short video as to why it is that things actually do float.
Why do things float? It depends upon two things: weight, how heavy something is, and volume, how much space it takes up. To understand why things float, it helps to understand why things sink. First, let's put a bowling ball in a bucket of water. Let's pause. The bowling ball and the water can't be in the same place at the same time. The water has to move out of the way to make room for the bowling ball. This is called displacement. It means being pushed out of place. So, as the ball goes down, it pushes the water up. Once the ball is completely underwater, it has all the space it needs. Then the water stops moving up. The volume of the displaced water is the same as the volume of the ball. But volume is not what makes the ball sink. The ball sinks because it's heavy. This bowling ball weighs 12 pounds. Water weighs something too. A bowling ball-sized chunk of water weighs about 10 pounds. The water wants to return to its original level, but there's a 12-pound bowling ball in the way. Since the bowling ball is heavier than the displaced water, the bowling ball has more sinking power. Now, what if we replace the bowling ball with something lighter, like a balloon? This balloon is the same size or volume as the bowling ball, but it weighs much less. Now we have 10 pounds of water pushing down on a very light balloon. The water is heavier than the balloon, so the water sinks, forcing the balloon up. Now the balloon is floating on top. Or is it? The balloon doesn't weigh much, but it does weigh something. If you look closely, you'll see it's displaced just a little water. The water it displaced weighs the same as the balloon.
So now we have the definition of a buoyant force. And a buoyant force is the upward force exerted by a fluid on an immersed object. They have this example of a swimmer pushing a beach ball underwater. And what happens is when you push such a beach ball underwater, you'll know from experience you need to really hold that beach ball down. And the reason for that is there's some buoyant force pushing upwards. It's the buoyant force is the upward force by the fluid on immersed object. It's this upward force. The way for us to calculate buoyant force is to use what's called Archimedes' principle. So Archimedes' principle tells us that the magnitude of the buoyant force on an object is equal to the weight of the fluid displaced by the object. So that's to say, if we look at the previous example, we have a buoyant force pushing upwards. If we would like to know how big that buoyant force is, then Archimedes' principle tells us that the buoyant force will be the same as the weight of the fluid displaced by the object. So that would mean that we would need to calculate what is the weight of water, a ball of water this size, what would its weight be? And that weight would be equivalent to the buoyant force acting upwards. We also prove Archimedes' principle. And the way we do this is by looking at a little block of the liquid, which is something that we've done before. And what we do is we look at the two forces. So we'll have a force at the bottom and we'll have a force at the top. And the buoyancy force is going to be the difference between these two forces. Pressure is equal to force over area. So force is equal to pressure times area. So we can rewrite each of these terms as shown here. We simply take out the area term in this line. Over here, we know that the pressure at the bottom minus the pressure at the top is given by the density of the fluid times G times H. So we rewriting this pressure difference as this. How do we know this? Well, this is one of the expressions that we saw previously. You remember we saw it in the form P bottom is equal to P top plus density GH. So that's where this equation came from here. Now we know that area, this area at the bottom multiplied by this height is going to give us volume. So these two terms here multiplied together give us the volume. And notice that if you multiply density of the fluid together with the volume of the fluid, then you're going to get the mass of this fluid. So capital M is the mass of the fluid displaced by the cube. So this is essentially the buoyancy force is equal to the mass of the fluid displaced by the little cube multiplied by G. So this is a mathematical proof of Archimedes' principle. Let's take a look at an example solving a problem using Archimedes' principle. So the problem states that a styrofoam slab has a thickness of 10 centimeters and a density of 300 kilograms per cubic meter. What is the area of the slab if it floats just awash in fresh water when a 75 kilogram kg swimmer is aboard it? So what we have is some styrofoam, some foam mattress, and it has a person sitting on it, and the person has a mass of 75 kgs, and the question says that the mattress is floating just awash. So that means that it's just submerged, and it's the top is flush with the surface of the water. And we asked to calculate what would the area of the mattress be in this case. So the way we do that is by starting with the fact that if we have a mattress, then there are a number of different forces acting, and the sum of the forces must be 0. So if we draw a free body diagram of, the man and the mattress, then the forces acting on it, the first force is going to be the weight of the man acting downwards. The second force is going to be the weight of the mattress acting downwards as well. Then you'll remember we have a buoyancy force. We saw in the previous slide that whenever we have an object submerged, so here we have a mattress submerged, we have a buoyancy force pushing it up. You can imagine if the man wasn't sitting on the mattress, then it would pop up right to the top, right? It would be caused by the buoyancy force. But in our case, the mattress and the man, they aren't sinking and they aren't rising, so we have the sum of the forces is 0. So the different forces we have is the buoyancy force acting upwards, plus B, minus the weight of the mattress that's acting downwards, minus the weight of the man. The sum of these forces must be equal to 0. What we can do is we can apply Archimedes' principle, and Archimedes' principle tells us that the buoyancy force will be given by this expression here. The reason for this is that the buoyancy force is the same as the weight of the mass of the fluid displaced. So the mass of the fluid displaced would be the volume of the mattress times the density of water. Together this would give the capital M from the previous slide. So that's the buoyancy term. Then we rewrite the mattress as the volume of the mattress and the density of the mattress times G. And for the man, it's just the mass of the man multiplied by G. If you look at how far we are along towards getting a solution, we already know that we're told that the mattress has thickness of T equals 10 centimeters, and I've called its area A, and A is actually what we asked to solve for. So we can rewrite the volume of the mattress as the area of the mattress, that's this A at the top, times the thickness. That will give us the volume. So we've rewritten this volume as the area times the thickness. Then we have the density. You can see that all of the G's have cancelled out. This G's gone, it's cancelled out with this G, this G. So we have no G's in the next line. Again, I've written the volume of the mattress as the area of the mattress times the thickness, and here we have the density of the mattress minus the mass of the man. Now we can rearrange to make the area of the mattress the subject of the formula. You can see it. The area of the mattress is in this term here and in this term here, but it doesn't appear in this term here. So I've taken the mass of the man to that side. I've taken the area of the mattress and the thickness out as common factors, and then I'm left with the area of the mattress is the mass of the man times the thickness of the mattress divided by the difference in densities between the water and the mattress. Substituting the values in yourself, then you'll find that the solution is 1.07 meters squared, which is the area of the mattress. Right, so that brings this chapter to an end. You'll recall that this chapter had a number of very important definitions. We derived an equation for the pressure at a certain depth in a liquid. We also looked at Pascal's principle and Archimedes' principle, and then we used those two principles to solve problems.